We'll now set about developing our material balances for our reactors. Of course, a real reactor may have a complex shape, it may have complex internals, and irregular flow patterns as a result. So the flow inside the reactor might not be what we expect it to be, or it may contain unexpected complexities. And this is going to influence the distribution of our concentration and our temperature. And as a result, it's going to become difficult for us to estimate the reaction rate. So for example, right here, if we have this oddly shaped reactor and we may have multiple inlet flows and multiple exit flows, we can imagine that the flow pattern here is going to be quite irregular. So there may be zones where the fluid is circulating, there may be zones where the fluid is flowing faster, and so on. And so we can imagine that the concentration is not going to be the same across the space. So for example, if we feed a high concentration of our reactant in here, then in the region close by this point, we may have a high concentration of that component, whereas by the time we reach the exit, we might have a higher concentration of the product and lower concentrations of the reactant. So certainly we expect that the concentration is varying across the space, and in a similar way, the temperature might be varying across the space. So we might be feeding the fluid in at a low temperature, and number one, we could feed one temperature here and feed a different temperature here. Then the reaction will be exothermic or endothermic, and so that's going to change the temperature in here. And so what exits the reactor will generally be different in temperature compared with the temperature at the inlet points. And so the temperature is also varying across the space. So both concentration and temperature are varying around here, and that's going to make it difficult for us to say there's one rate. We know clearly there will be one reaction rate here, which is quite different to the reaction rate here. And so this entire space is a continuum of reaction rates. So that's why we say here the reaction rate is a function of x, y, and z, so that's varying across the space. And then we expect that it may be varying in time as well. So we may have a certain concentration profile in this reactor at the start, and then as we change the flow rates here or the concentrations in these feed lines, that's going to change the concentration over time as well. So this is really a four-dimensional variation in concentration and temperature, and hence the reaction rate. So this is quite complicated on the face of it. And the typical way that we handle such complexity in engineering is we partition the space. So if you see these little boxes drawn in the space here, these boxes are little differential elements. So they aren't real boxes that are sitting in the reactor. Those are conceptual boxes. Those are where we can imagine that, yes, this is a complex shape in our reactor, but we can identify perhaps 1 cubic centimeter in our reactor. The reactor might be 100 cubic meters in size, but we can think of a particular fluid element in the reactor or a specific space in the reactor, and we can point to that space and say, there's 1 cubic centimeter of space in that reactor. So if you like, it's a fixed little floating box in the reactor. So not floating in the sense that it's moving with the fluid, but floating as if it's a fixed point, fixed point or a fixed sub-region inside the space of that reactor. So we imagine a fixed volume in that reactor without boundaries. So there are no real walls to this space, the subspace in the reactor. And then we can imagine flow across that space. So we can imagine if the fluid is flowing past the space or through the space, this ghost space, if you like, then fluid is entering here, fluid is leaving from the space, and in the space, the fluid is still reacting. So the fluid is always reacting throughout the volume, and we are now just looking at a specific sub-volume of the space. And so we are sketching out here, apart from the reactor, we are sketching a specific sub-volume of that reactor, and we are choosing this to be deliberately small. So if you imagine the dimensions of this little imaginary box, delta x, delta y, delta z, and if we imagine those dimensions shrinking down to 0. So I said a cubic centimeter, but we are looking much smaller than that. We can talk about microns or even down to angstroms. So we are imagining a differential element or a differential space inside our real reactor. And so the point of that is it's so small that within this little box, we can say that the reaction rate is not a function of position. So in contrast with this large volume here, where there's enough space for gradients to develop. So this is big enough that we can say the concentration here is different to the concentration there. By contrast, we are looking at a much smaller subvolume, and this is too small. So this is small enough that we can say approximately the reaction rate is the same at all points in this little subvolume. So we can partition our space into smaller spaces, into millions or billions or trillions of subvolumes, and we can say that within each of these tiny subvolumes that we have the same reaction rate at different points in there. Now, of course, we've only talked about spatial discretization. So this is discretization. We break it up into discrete volumes. So we've discretized in space. We haven't discretized in time. So we haven't said that we are only thinking about a tiny change in time. And so it's this box only exists in a very short-lived instant in time. So we are not saying it's constant with respect to time. So over time, the concentration and the reaction rate and so on will vary in the subvolume, but in terms of space, there's no change from one x position to the other x position and so on. So that's our subvolume. And now we can think about writing a balance on the subvolume. So we can say that, fine, all this complexity is happening in this overall reactor, but by the end of the day, there's a certain total amount of flow into the space, and we can just add up all these streams. And we can add up specifically the molar flow rates in these streams, and we can subtract out the molar flow rates in these streams. So we can define for ourselves the total number of moles of some component in this reactor. So let's say we are considering component I, then we can define n sub I to be the total number of moles in the reactor. So we're not talking about subvolumes now, we are talking about the entire reactor space, that there does exist. We know it's varying from point to point, but there does exist a certain total number of moles inside this entire reactor, and we are saying we define that number to be n sub I. Right, so that's the total number, and that total number is changing over time, and that's changing with time because, number one, we keep feeding more of component I in here, and we keep withdrawing more of component out here. So we would say that the rate of change of component I in the space, right? That's what we're saying here, ddt, the rate of change of component I, the rate of change of the number of moles of component I, that's equal to, and that's equal to a contribution from the inlet streams. So we can add up the inlet streams to the space. So we can say the total amount of I flowing into the reactor, and then we subtract off the total exit or withdrawal rate of component I. So adding up all the exit streams, we can say minus Fi out. And then component I is also reacting in here. So it might be that component I is being consumed in the reaction. It might be that component I is also formed in the reaction. And like we said last time, we have defined Ri on a volumetric basis. So Ri is the rate of formation of component I. So generally speaking, we can say now we can look at the subvolumes, right? Ri by itself is complicated. We know Ri is varying across the whole space. That's what we said at the outset. However, we could just go and work out Ri in each of these little boxes. So at some instant in time, there exists a certain reaction rate, Ri, inside this little box. So that's just one little box. So we can say there's a contribution to the rate of formation of component I from this little box. And then we can just go ahead and add up all the little boxes in the space. And we do have to include all of them. The smaller we make all these boxes, the more there will be of them. And all those boxes have to be consecutively positioned. So when we discretize the space, we form all these boxes that are lying immediately adjacent to each other, and that might be above and below and to the side, to both sides, and on the face closest to us. So if you imagine a cube, so on every side of this cube there's another cube lying there, and so that's how, except at the boundaries of course, and so that's how we fill the space with these little boxes. And we had defined the reaction rate to be a volume-based thing. And now we've defined the reaction rate for all these little boxes. So we need to add up the rate of formation of component I for each box J. So J is the box number, if you like. So we are adding up the reaction rate over every single box. And the reaction rate, we had defined the units for this to be moles per second per cubic meter. Now, if we look at the other variables here, this is number of moles, and then this is per time. So this is moles per second. This, we said, is a flow rate, a molar flow rate. So this is also moles per second. So we've got moles per second, moles per second, moles per second. And now here we've got moles per second per cubic meter. Well, we are multiplying then by the volume of each little box. So we said J is the index of the box. So if we just take the reaction rate in the box and multiply it by the volume of that box, then that is in moles per second, the contribution from the rate of formation of component I. Right, so we add up all the boxes times the reaction rates in all the boxes multiplied by their volumes, and that gives us the molar rate change due to reaction. And by the way, we've said Ri is a rate of formation, and so of course there's a number behind this. So if, for example, it's 10, then we are saying we've got 10 moles per second per cubic meter. If component I is actually being consumed in the reaction, so if I is a reactant, then it's going to be consumed. In that case, the number will be a negative number, so it will be minus 10 or something like that. So that's the convention we adopt, that Ri being a rate of formation. If it is a formation rate, then the number is positive, and if it's a consumption rate, then the number will be negative. And so we don't have to worry about that anymore. We can write a nice general equation here without worrying about the sign here, whether I is actually a reactant, and we don't have to worry about that. We know we take account of that through the value here, whether it's positive or negative. So anyway, if we look at this whole balance, you've got in the space, there's a certain total rate of change of your component I number of moles, and that is a result of, we've got flows coming in, so we add up, so the rate of change in the space must equal the rate due to the addition of component I here, minus the rate due to removal of component I here, plus the rate of formation of I across this entire space. So all the complexity that we had discussed earlier is now allocated, if you like, into this reaction rate contribution. Okay, so that's how we can think of this material balance over this complex space. And if you like, as we just said, we have just lumped all that complexity behind this. And in this session, we'll look at unpacking that complexity and think about how we can estimate the numbers there. Because at this stage, we don't know how to do this, right? At this stage, we can think, yes, I could imagine that I would know how much I'm feeding in here. So I know, for example, that I'm feeding 20 tons per day into the reactor. And so I know I want 20 tons per, or maybe it's 15 tons per day of the product coming out here, plus 5 unreacted tons of reactant. So those are things we can imagine. Yes, we can get numbers for these. So we are in control of these. We can specify our production rate that we want. We can specify how much we are going to pump into the reactor, but we don't as yet know how to estimate the reaction rates here. And then this is just a little note that this is talking about discrete boxes. But of course, if you think about the differential form, and if you think about your calculus, a better way to represent this is as the integral of a field Ri with respect to V. So instead of trying to discretize the space and then go and add up all the little boxes, we can more compactly write this as the integral of R with respect to the volume, where volume V is a variable across the space. So when we use V here, we are not talking about the total volume out here, right? So for this real reactor, maybe the volume is 10 cubic meters or something like that. That's not what we are saying here. This volume is more specific. It's saying within those that 10 cubic meters, we can, if we look at a specific space, then that's a specific subvolume. Maybe this is 10 to the minus 9 cubic meters or something like that. So V is V here. So that's in terms of dV. And here V is referring to the specific location inside of this volume. So here we are thinking of V as a variable that goes around the entire volume. And so as we move around the volume, we add up all the contributions, and that's going to estimate for us the total influence of reaction on our overall material balance. Right, so that's where that material balance comes from. And then it's written more cleanly here. It's the exact same equation, just reproduced here. Okay, so now we want to unpack this, and then we've talked about the units here, right? Ni is number of moles, T is time in seconds, Fi is moles per second, molar flow rate, Ri is our standard definition for reaction rate, moles per second per cubic meter, and our volume is in cubic meters. So as we said, we don't know how to solve the equation because we don't know this function. We don't know how R is varying in T and X and Y and Z. So we don't know how to evaluate this. So right now, this is just a framework. This is an abstract expression showing us how we would go about writing up this balance. And to make some progress, what we have to do is talk more specifically about the reactor and how the fluid is flowing through it. So to begin with, let's define for ourselves the batch reactor. So here's a nice little symbol for it. So a batch reactor, as the name implies, is one where we charge the reactor with our reacting components, and then we close it off and we have no further flow through that reactor. So it works in batches. You put your reactant in, you close the reactor off, and then you allow the material in here to react, and you hope that your reactant is going to be converted into your product. And you can see here there's this agitation, so it's not just to show that, oh, sometimes we go and mix up the content of this reactor. This is also symbolic. When we draw this, we typically take this to mean that there is strong agitation in this reactor, meaning very strong mixing. And so this reactor is going to be what we call perfectly mixed throughout its operation. So it's not the case that you'll be able to find a location here where the concentration is 10 moles per cubic meter, and here it's 50 moles per cubic meter. Because it's perfectly mixed all the time, we have one concentration at all points in this reactor. So that's a considerable simplification compared with what we were just talking about. So here we said the concentration could vary at all points across this. Now we are saying, no, it's perfectly mixed everywhere, so we've got the exact same concentration at all points. That also applies to temperature. So if it is perfectly mixed, when we say it's perfectly mixed, we typically mean in both of in terms of both concentration and temperature. So we've got the same concentration everywhere, and we've got the same temperature everywhere. So that means we've got the same reaction rate at all points in this reactor, and we've stated that by drawing it in this way, by drawing this agitator. So now we've got this general framework which works for everything. Now let's think about how this equation would change under these conditions. So first of all, let's think about this term. the total number of moles of component I. So this is a balance specifically on the ith component in the reactor. Now, for example, if it's a reactant component, then that component is going to disappear over time. So we acknowledge here that this rate, that this change in the number of moles of I, that is likely to go on. That's likely not to be zero. So we can't cross this off and say, oh, that's a zero, right? Component I is changing in time, right? That's the purpose of the reactor. We want to convert component I, and so we retain this term as something that's not going to be zero. On the other hand, if we look at the flow terms, we said these were the molar flows into and out of the reactor, and now by definition it's a batch reactor. After we've initially charged the reactor with our reactants, there's no further flow in or out, so both these terms will be zeroed off. So we no longer have flows through the system, so we can, not ignore, we can cross these terms off as identically zero because there's no flow through the system. So those are the first three terms. And then in terms of this one, we've said now that the concentration and temperature are the same at all points across this reactor. If that's the case, then the reaction rate is also going to be the same at all points in this reactor. And that means that this reaction rate is not going to be a function of the volume position. If you like, the volumetric position. Ri is not a function of V. It's not zero, but it's not a function of V. In other words, it's a constant number with respect to volume V. So we can take this Ri out as a constant of integration, and then it's just the integral with respect to V over the total volume V. In other words, this is just going to become Ri times V. Right, so that's we've said all this here, and so you can read all this, and so the balance simplifies just to this form, right? As we said, we retain this term, we zero out these terms, and this is simply RIV. And so if you put all that together, that is the balance on this reactor. Okay, and then we note that by definition, concentration is the number of moles divided by the volume. So if we just divide by volume on both sides here, noting that we are assuming volume to be constant, right? So if, for example, this is a gas phase reactor, then the gas is going to fill the entire reactor, so that's the reacting volume V, and that's going to be constant. It's going to be the volume of the vessel on the inside. If it was a liquid reaction, if it was happening in the liquid phase, then there'll be some liquid level, and if it's operating in batch mode where we aren't feeding liquid in or withdrawing liquid out, then that level might stay constant, and so the volume of that liquid is going to be a constant. So V is a constant, and so we can just divide through by V on both sides, even inside of this, and so here this from the definition of concentration, this becomes dCi dt, and here we are just left with Ri. Right, so that's the balance. That's our batch reactor balance, and this is then a simple first order ODE. And if we have an initial condition, in other words, if we know the concentration of component I at some instant in time, so let's say Ci0 was our initial concentration in the reactor, then that's our initial condition, and we can solve this equation then, and we can get the concentration as a function of time in that reactor. And so for our first tutorial, here's the exercise. Please develop your batch reactor balance, and by the way, please do it from this form. All right, so start with your basic balance, develop your batch equation, and then write this equation for each of the components. And we are given more data here. It's a 5 cubic meter reactor initially with 10 moles of SO2 and 10 moles SO2 and 10 moles of O2. So that's not a stoichiometric ratio. We are given the rate constant. And we haven't really talked about that, so let's see how to use this so-called rate constant. So if the reaction is elementary, and if the reaction looks like this, 2SO2 plus O2 giving us SO2, SO2. We said that if it's an elementary reaction, then simply R equals, well, let me do it like this. R equals K times C sub SO2, and this is going to be squared. So remember, we said the stoichiometric coefficient becomes the power of the concentration, and then multiplied with the concentration of O2, C sub O sub 2. Right, so that's the reaction rate expression. And in the problem, we are told the value of the kinetic rate constant. So we are given the K, and then the concentrations are actually the variable of the equation. So if we look here in the notes, what we said is this is the balance. And so, for example, if we are writing the balance on SO2, then we would write dC sub SO2 dt equals, and then it's R sub SO2, and that's going to be this thing, Kc SO2 squared CO2. And now you can see CSO2 is the variable of this equation. Right, so you've got the variable of the equation, and that means we have to solve it. We also need the concentration of O2. So we need also a balance here. dCO2 dt. And let's say we don't want to reevaluate this this reaction rate. So we have our SO2, and we can say, well, O2 is consumed half as fast as SO2. So we can just write here 1/2 times our SO2 is equal to K/2 here, and so that will give us CO2. So we solve these two equations simultaneously, and that means at every instant in time we'll have a number for CSO2 and a number for CO2. So these two balances are sufficient for us to solve this problem. So I'm just explaining it at a conceptual level right now. We'll go into more detail in the tutorial in how to solve these balances using numerical methods and so on. So just in terms of the concept, which is where we want to keep this lecture, we can just use repeated applications of this overall balance, and we can substitute our reaction rate expression. So in all the steps, there exists some reaction rate, and we need an expression for this. And so in this case, we were given the rate constant, and we were told that it's elementary. Yes, it says here reaction is elementary. So when it is elementary, then we know how to we know the functional form for this. We know it's not CSO2 to the power of 5 and with no CO2. We know for elementary reactions it's C of this raised to the power 2 times C of this raised to the power 1. So that's how we got the form of the equation. And then we've got this as a number just given to us, and we know this is these two are the variables in the balances. So that's enough to go ahead and solve that equation. Okay, so that's how you do it for the batch reactor. So very straightforward. There's almost no development that we've done here, although this concept of perfect mixing is something that we are going to use again just now. Well, in fact, right now. So the next step now is to consider a continuous stirred tank reactor, CSTR. Please note this is not continuously stirred tank reactor. If you said continuously stirred tank reactor, that means it's being stirred all the time. And that's not what continuous means in this context. So we are saying continuous because of the flow. We have a continuous flow through this reactor, which is not the same as in the batch reactor. There was no flow through this reactor, so it's not continuous. This one, it's continuous flow stirred tank reactor, if you like. So CSTR, that's the established terminology, and don't be misled by what that continuous means. So in this case, again, we have perfect mixing here, so we are going to have the one reaction rate across this reactor, but this time we have flow as well. So going back to our balance, so the overall balance that applies to all reactor types, well, here I can see I've cheated a bit, and I've already used this assumption of perfect mixing. So yes, it is, we do make a note of it here. So we are saying, yes, again, it's perfectly mixed, so the reaction rate might not be constant in time, but it is definitely a constant with respect to volumetric position. So we can replace this by RIV, so that's there. And that's the form that we have right now. And again, we can think about dividing both sides by V and working in terms of concentration. We know the reaction rate expression is going to be in terms of a concentration. So we know that we will replace that, and we would like to write all of this in terms of concentration. So in the earlier one with the batch reactor, we can see that if we replace Ri by a function of concentration, then it's one equation in one variable, concentration. But now we have these extra flow terms. So we need to think about how to express this in terms of concentration as well. So, of course, though, these are molar flows. And so the molar flow rate is nothing but the concentration multiplied by the volumetric flow rate. Right, so this is moles per cubic meter. This is cubic meters per second. So the product of these two is going to be moles per second. So, well, that's just talking about the units. So we can see the units at least agree. Multiplying these two will give us moles per second. And just conceptually, the concentration in the inlet stream, so in the stream, there's a certain concentration here, which is generally different from the concentration here, which is different from the concentration here. So the concentration here, C in, multiplied by the volumetric flow rate of the stream, Q in, that must be the molar flow rate into the reactor. So that's Fi in. And then in a similar way, we can look at the exit point and say, well, there's a volumetric flow rate here, Q out, and then there's a concentration in this exit line here as well. We know that concentration is influenced by what's happened in this reactor, but whatever it is, we can define for ourselves a concentration here, Ci out. So the molar exit flow rate is equal to Ci out times Q out. So that's how we translate these F's into concentrations. We expect that the N we can relate to a concentration in the same way Ni equals Ci times V. So anyway, that's what we do here, right? So the number of moles equals the concentration in the reactor multiplied with the volume. And again, there we want to be careful. The concentration, as we said, is the same at all points in this because it's got this perfect mixing going on. So perfect mixing, that means we've got the same concentration at all points in this reactor. So the total number of moles of component I in this reactor is the concentration of component I, which is a single value across this reactor, multiplied by the total reacting volume. So that's there. And then we've just established all this. Now, one more thing to think about is, well, we've said in the exit stream, we require this specific concentration Ci out, and we know it's influenced by what's going on here. And if you think of it, this is nothing but, if you like, a sample from the reactor. So we are constantly withdrawing a stream from the reactor. So the concentration in this stream must be identical to the concentration right next to this point here. So at the exit point from this reactor, there exists some concentration inside the reactor, and that concentration must be identical to the concentration in the stream. It's the same. It's the same fluid that's flowing through here. So that's a concentration just inside the reactor. Now, at the same time, it's perfectly mixed. So the concentration at this point must be identical to the concentration at all points in this reactor. So that's why we can say the concentration at the exit point is identical to the concentration inside the reactor, which is just one value now, Ci. So we can simplify our balance further. We don't have to write here Ci out, which is yet another variable. We can say instead Ci, which is actually the variable of the balance, right? Ci dt, that's what we want to solve for. And then, of course, we retain the reaction term, and the reaction rate is constant, so it's just Ri times V. We don't have to integrate over trillions of little spaces. So that's our overall balance. And in this form, it's already quite usable. You can solve a balance like this. There's no problem with working with this balance. Of course, we have to unpack the reaction rate here. And like we said in the example, the same rate expression applies. So this is dictated by nature, right? Nature tells us if you have SO2 at this concentration and oxygen at this concentration, then this is going to be the reaction rate. So this is totally not dependent on where this reaction is happening. So it doesn't matter to nature whether the reaction is happening in this CSTR, or whether it's happening in a batch reactor, or whether it's happening in a little puddle on the ground somewhere. As long as those concentrations apply, then nature has its rules, and it says, well, then this is the rate at which everything's going to react. So we unpack the Ri term in exactly the same way for the CSTR as we did for the batch reactor. So that's the balance we have now, and so we can go ahead and solve this. We can get numbers for everything in here. We prescribe the flow rates, so we as engineers we are pumping in 50 cubic meters per day, and we are withdrawing from the reactor so many cubic meters per day. So we can set those numbers. We know we are pumping in component I at a specific concentration, and then Ci is the variable, so that's what we are solving for, and Ci is also behind Ri. The volume of the reactor, as engineers, we can stick a level in there and say, oh, the tank is 4 meters high today, and it's a cross-sectional area of 2 square meters, and so it's overall 8 cubic meters, whatever. So we can get these volumes. So I'm trying to say here, all the variables can be identified. We can get numbers behind all of these. Only Ci is unknown, so we can just go ahead and solve this balance, and we can get that. Of course, we need the initial condition as well. So this is an ODE, a first order ODE in time. So that means if we can get the concentration of component I at some instant in time, then we can just integrate forward and backwards as well, and find Ci as a constant as a function of time. Right, so we can work with the balance like this. However, it is possible to further simplify this, and well, not exactly simplify. We can think of specific scenarios. We can think of a context when some of those terms further simplify. So, for example, up to now we've just said Q in and Q out are the flow rates, and we didn't say what their relationship was. So if we had this specific instance when the flow rate in was equal to the flow rate out, right? And there's no requirement for us to do that, but we are saying if we operate in this way, and we think it's a good way to operate, because we would like nice stable operations. We don't want to be blasting in more of the liquid than we are taking out, because we know then the tank is going to overflow. So we want things to come to a nice stable operation. So it's likely that we would try to set the inlet flow equal to the outlet flow, and then and so we can replace Q in and Q out by some constant Q. Well, this doesn't have to be constant. We are just saying these are equal. They are not necessarily constant with respect to time. So over time, Q in, it could go from 5 to 10 to 15. And then if we've set that they are equal, then at the same times, Q out must also go from 5 to 10 to 15. So we are saying they must be equal. And so as long as these two are equal, the volume will stay constant. So again, if you have your reactor here and you are feeding at a certain volumetric flow, even if you are changing that flow over time, as long as you are keeping these two things the same, then if whatever level you have here, it's going to stay at that level. So even if you suddenly ramped up by 10 cubic meters per second the flow here, if you are also suddenly withdrawing an extra 10 cubic meters per second here, then that's not going to disturb the level. So your your volume is going to be constant in that case, and so when those two are equal, the volume is constant. Then we introduce this definition. We are going to say tau equals V over Q, the volume of the reactor divided by the volumetric flow rate. And this tau has a lot of meaning, which we'll discuss later. But for now, let's just take it as a definition. There's nothing to say. There's nothing to stop us just deciding to make a new variable to say that's the ratio of volume to flow rate. So V over Q is tau. And so if we stick all that in, so going back to our balance, so we had said here we've got Q in equals Q out equals Q, so we can make both these Q, and then we can group the Q's together. So that's your volumetric flow rate Q, and you've got RIV here. So we can go ahead and divide through by volume, and just be careful when you've got a variable that you want to cancel, and if that variable is sitting inside a derivative, you want to make sure that this variable is not a time function. And in this case, we established that volume V is a constant, so it's valid to go ahead and just divide everywhere by V. So if we do that, it's vanishing here, and then we've got Q, so it's going to be Q divided by V, and we've divided here V divided by Q as tau, so this is going to be a 1 over tau. So this just becomes Ci in minus Ci over tau, and then the V is cancelled here. Here you can see I'm emphasizing that tau might be a function of time, and that's because, right, we know V is not a function of time, it's constant, but Q might be changing with time. So we said Q in equals Q out, but Q might be a time function. So tau might be changing because Q might still be changing. So in that case, tau is a function of time. It's not that it crashes our equation or anything. It just means we might need a time function here. So this is a simpler form of the equation than we had before, and this is suitable now for the case where your flow rates are equal, and you can definitely solve this equation in time. There is possibly another variable that changes in time, so your inlet concentration might be varying in time. So you might choose to do that if you were trying to control this reactor, or let's say you wanted to change your product specs. So if you were feeling that, well, maybe my production rate or my concentration of product here is too low, then you might want to try to increase the reactant concentration. So you might ramp up, you might change the inlet concentration over time, and so influence what's happening here, which is fine. There's nothing wrong with doing that. So if that's a function of time, then that will also play its role here in this balance. So anyway, this might still be an unsteady state equation in time. Now if we say the flow rates are equal, which is what we did here, but they are also constant. And when I just say constant, I mean in time. Normally I say, when I say uniform, that means across the space it's the same. When I say constant, I mean it's the same in time. So uniform and constant, those are for the space and time, right? So uniform for space and constant for time. So the flow rates are equal and they are not changing in time, and the inlet concentration is also not changing in time. So if that's the situation, right, if your flow rate, if these two are equal and they are constant, and your concentration here is constant, then we can easily imagine that this whole reactor is going to reach a constant state of operation. It's going to reach a constant concentration in here, and you will be producing your product at a certain constant rate here. And so that doesn't mean that nothing's happening, right? We can still form our product. We are still forming a product. We are still converting a reactant to a product, even though we've reached a kind of constancy here. So if we are feeding, let's say, 50 moles per second of a reactant here, and we are getting 40 moles per second of product out here, plus maybe 10 moles per second of unreacted reactant, right, then that can all happen steadily. So we can say we reach a stage where it's stable, it's steady state, and it's just constantly forming new product, and that new product is constantly coming out here. So that's how we can have a production rate that's maintained even though the system is at steady state. So you've got fixed flow rates here, and you've got a fixed concentration in here. And so the system, we can imagine, is going to reach a steady state. You will steadily be producing a product, and you'll steadily be sending that out here. So that's steady state in the CSTR. So if we are at steady state, then this becomes zero, right? The concentration in the reactor is not changing with time. Doesn't mean product is not being formed. It just means that it's being formed so steadily that if you were to look at the reactor, you will see in that reactor a constant amount of product. So even though you are constantly drawing product out of the reactor, still the amount that's in the reactor is constant, and that's because we are constantly feeding reactant, and that reactant is constantly being converted to product here. So it's important to understand it in this way, that steady state still means that the reaction is happening, right? On the other hand, if you think about it from the perspective of a single molecule, so if one molecule is coming in here, then it reacts with something, and then it's converted to something, and it goes out here, then from the perspective of that molecule, it's not constant. From that molecule's perspective, it's experiencing a change over its own lifetime. But we are not dealing with single molecules here. Here we are dealing with a constant flow, a constant stream of molecules, a constant exit flow of molecules, a constant conversion of molecules. So we reach a steady operation in the reactor, and that's steady state. If you can understand that well, many concepts in chemical engineering and in engineering in general will make much better sense. So we reach steady state. We can neglect the accumulation term, and then we can take this thing across to the left-hand side, and we can say this. So this is now the balance at steady state. So it's telling us that depending on the reaction rate, there will be a certain fixed amount of concentration in the reactor of component I. It's also influenced by the space, this is called the space-time. So by this mysterious number so far, V over Q. So that's how we can solve for the concentration in the reactor. And by the way, so just remember this, you've got some difference of C over tau equals R. And if you go back to our batch reactor, you have some difference of C, right? This dC is a differential change in C, divided by change in time. So not tau in this case, it's delta time. So in the batch case, delta C over delta time equals R. And in the CSTR case, we've got delta C over something that looks like time divided by, equals to R. So there's some similarity between this equation for the CSTR case and the equation we got for the batch case. Anyway, we'll come back to that. And then going a bit further, we want to try and understand this tau a bit better. So we had simply defined tau as V over Q, as if it's just some convenience variable as the ratio of V over Q. But let's think about velocity, for example. So velocity is, if we think about some object moving at velocity u, then its change in z position. So it will change its position, and let's say z was the position variable. So the movement in z divided by the time taken for that movement is the velocity. Now, in a similar way, we have, in our case, volumetric flow rates and volumes, and we've defined this tau. So we said tau is V over Q, or we can write Q equals V over tau. So we can say volumetric flow rate is analogous to velocity, and volume is analogous to a spatial position. So in other words, this tau is something like the time. So the time taken for a certain volume to, the time taken for a certain volume to be traversed at this flow rate. So for example, if you can imagine you want to move 50 cubic meters, and this is a 1 cubic meter reactor, then so if your flow rate is 50 cubic meters per hour, then clearly if this is a 1 cubic meter reactor, then it's going to take you 50 hours to do that. So the volume, 1 cubic meter, divided by the volumetric flow rate, 50 cubic meters per hour, that's going to be the number of hours it takes to pass through this volume. And sorry, I said 50 hours, but it's 1 over 50 hours. That's the time taken. If our flow rate here is 50 cubic meters per hour, that means we are pushing many, many cubic meters per hour. So anyway, that's the meaning of this variable tau. So we call it the space-time, and we can see it relates to the average time that our fluid is spending in that reactor. So you can think about the analogy with velocity, and you can understand this tau. And here, just a comment on the units, if you like. We know Z being the spatial position is in meters, time, of course, in seconds. So this is meters per second. We know that those are the units of velocity. So here, if volume we know is cubic meters, and volumetric flow rate we know is cubic meters per second. So cubic meters over cubic meters per second is going to give us back seconds. So tau at least has the units of time as well. So it's a different kind of time. It's the time of the average fluid. It's not the time of a specific object. So that's how we can understand the so-called space-time variable tau. Okay, and there's the example now further developed. It's the same reaction set, sulfur dioxide and oxygen to give us sulfur trioxide. Similar values to before, 10 moles, 5 cubic meter reactor, same kinetic rate constant. So now you go ahead and do this for the CSTR, and you can do it. There are some comments here on volume expansion, which we'll get to a bit more in the next one. Now, now we come to the third type of reactor, the so-called plug flow reactor. So this is a conceptual approach. It's, if you like, a hypothetical case where your fluid is flowing in discrete groups, or rather the molecules of your fluid is flowing in discrete groups, and the molecules in one group don't communicate with the molecules in the other group. So they don't mix or transfer or react with in any way the other group. So for example, so that's talking almost like in terms of groups. It's fairly abstract. It's an abstract way to say it. But if we imagine a cylinder, so let's say the reactor is a cylindrical object, and we are pumping our reacting fluid through this reactor. And we've got here 2 plugs. Right now, When I say plug, I just mean a collection of molecules. So it's an imaginary plug. It's by no means some kind of specific thing that you can identify in the reactor. So we can just imagine one group of fluid elements, let's say on this side of the reactor, and another group on that side. Then under this model, there's no communication, there's no contact between the molecules from here and the molecules over there. And this is in direct contrast to our CSTR type model. So in the CSTR, we said this was perfectly mixed. So we had such strong agitation that any molecule at any point could see every other molecule in that reactor. So we had one concentration everywhere. Whereas here, we've got distinct zones in this reactor, if you like. And so we can imagine this one is reacting at one rate, and it may be different to the reaction on that's over here. And so there will be a difference in reaction rate axially across this reactor. And it may be thought of as the exact opposite case to the CSTR. So in the CSTR, everything, if you like, is mixed laterally. So if this was a tube like this, then to achieve a CSTR-like behavior, we would have to have lateral mixing, infinitely fast lateral mixing. In this case, in the plug flow reactor, it says it's not traveling or it's not mixing laterally. So it is flowing laterally. So your fluid is flowing axially down this tube, but it's flowing at a finite rate. So there exists some velocity here, and that velocity is a fixed number. So it's some finite number, maybe 2 meters per second or something like that. So you've got a plug of fluid, and well, you've got multiple plugs of fluid. At every axial position, you can imagine a different plug. And each plug is passing through here at some fixed velocity. And the important bit is that there's no transfer of the molecules in this plug. So when I talk about a plug of fluid, there's nothing to stop us saying, all right, I don't know what molecules are in there, what collection of molecule types are in there, but I can see there's a liquid. I can imagine a disk of liquid here in this reactor. So this disk of liquid, as we observe the disk moving, so there's an imaginary disk that's moving with the fluid. We can easily imagine that molecules from inside that fluid are then diffusing out of that disk and then becoming part of other disks and so on. But that's not what's happening in a plug flow reactor. In a plug flow reactor, we are saying that all the molecules in each disk of fluid are staying in that disk, and they are only reacting in that disk. So that's the name, a plug flow reactor. It flows in plugs, and each plug is its own entity, and it has all its behaviors internal to that plug. And if you like, that's the perfectly not mixed case. So we had the perfectly mixed case here. Every molecule was mixed identically across that whole reaction space, so you had one concentration everywhere. In this case, it's perfectly not mixed. Every molecule is held in its own individual space. It's chugging along with its peer molecules, if you want, and they're all coming in at the same time. They'll all spend the same time here, and they'll all exit at the same time. So that's the case of the plug flow reactor. Let's just see here. We've said this. So no axial movement of the molecules. Well, the molecules are moving axially, but they are moving with their group. So there's no superimposed movement of molecules outside of this plug. So the molecules remain in the same group of molecules as when they first entered. Any reaction is within this group. And then on the other hand, each group of molecules is perfectly mixed. So in this plug, in this group, every molecule is perfectly mixed. So for example, radially, right, if this is a tube, then radially these things are perfectly mixed. So they're not mixed in this direction, but they are mixed in this direction. And so, well, that's what we just said. And then yes, you might think this is an unlikely situation, that it's hard to accomplish such a kind of behavior, that it's hard to stop molecules diffusing around. And definitely you can't stop them diffusing around. But if you have a high enough flow rate here, right, if your fluid is passing through this reactor fast enough, then it's possibly the case that there isn't as much time available for diffusion to deform where the molecules are sitting. So imagine a high flow rate through this reactor. Then on average the molecules will stay close together and they won't communicate with the other groups. So so that's the other extremum, and that's why we are doing this, right? We've got perfectly mixed case CSTR, batch reactor, that's all perfectly mixed, and we are able to develop equations and we are able to solve those equations. Now we've got the perfectly not mixed case, and if we can solve those equations, then we have the two extrema. So these are both unlikely situations. It's unlikely to get one perfect plug all the time, right? So it's hard to accomplish that in the real world. And in a similar way, in our CSTR, it's very hard to get perfect mixing the way we mean perfect mixing here. Yes, you can stick a stirrer in and agitate as much as you want, but you won't get infinitely fast mixing, which means that every molecule can instantaneously and always see every other molecule. So that it would take an infinite amount of energy in the real world. Nevertheless, we go ahead and make that assumption and we use it. And it turns out to be a fairly good assumption in specific cases. But more than that, it's giving us an extreme situation. It's giving us extreme perfect mixing. And in this case, we are looking at extreme perfect not mixing. So we've got these two extrema which don't occur in the real world. The real world is somewhere between these two extrema. And if we are able to develop models and equations describing these extrema, by combining them, as we'll see later on, we are able then to predict what actually happens in the real world. So that's why we are doing this. It might occur to you, none of this is ever actually happening. Are we just doing this for some academic fun? At least I find it academically fun, but it's more than that. You will see that there are intense practical reasons for doing this later on. So anyway, we've got this idea now of perfect mixing, and we need to take it beyond an idea. Let's see if we can create a model out of that. So how does this thing behave if we were to draw out material balance? So first, let's define the volumes. So we've got this tube here, and we are defining two axial positions in this tube. So we can imagine at some position Z down the tube, there'll be some flow rate there. And then we can imagine a little distance past that, delta Z. So we've got a second position, Z plus delta Z. So we have defined for ourselves now a nice little volume inside of this reactor. And we want to write a balance on this little space. And the way we'll do that is actually by using our framework. So we have this general balance that applies to everything. And fine, now we are looking at a little volume Z to Z plus delta Z, but still there's nothing to stop us using this. We had no restrictions when we created this balance, right? When we drew it out, we said, oh, it could be this weird shape and it may have multiple flows and so on. And now we are just saying, well, this weird shape we are going to specify now is just this little disk that goes from Z to Z plus delta Z, and it's got to flow in and flow out, a single flow in and a single flow out, I should say. And so now when we look at it, we are just writing a balance on this. So we aren't as yet talking about what's happening to the left and right of that disk. So let's just write the balance on this disk and see from there. So if we go back to that original balance, we know we've got dN dt on the left-hand side. And now just to remind us that this is written on this volume between Z and Z plus delta Z, I'm writing this here. So I'm saying this is dNi dt at Z to Z plus delta Z. And then arriving in to this, right, is the molar flow rate at position Z. So here we are pretending now that there exists an actual reactor here and that it has an inlet flow and an exit flow. And the inlet flow is actually due to the flow of the reacting fluid through this tube. And so the reacting flow through this tube, it's going to reach position Z at some stage, well, at position Z. And then by definition, the molar flow rate there is Fiz. So we are saying the molar flow rate of component I at position Z is Fiz. And so that's the flow into this defined space of interest to us. And then we'll have a flow out of the space as well. And so at position Z plus delta Z, that is the exit from this disk. And at this position, we also know there's a molar flow through the space here. So that's going to be Fi at Z plus delta Z. And by the way, these two numbers are not generally the same. So remember, these are molar flows. These are not volumetric flows. So the way I'm pointing here, you might have thought, isn't this just, that's 5 cubic meters here and another 5 cubic meters going out there. So we are talking here about the molar flow of specifically component I. So yes, the fluid is being carried through, but arriving here might be 2 moles per cubic meter of component I. And then maybe I is reacting here and coming out here is 1.8 moles per cubic meter of component I. So these are generally different. Your number of moles of I is changing as it flows through this reactor. And that's just by virtue of the reaction itself. The reaction is consuming or producing I. So each time you shift, you look a little distance down the tube, I has reacted a bit further. So anyway, that's flow in and flow out. And then the reaction itself that happens in this space must be the reaction rate multiplied by the volume of that space. So the reaction rate at position Z, or between Z and Z plus delta Z, I'm writing it like this. So this is the rate of formation of component I between position Z and Z plus delta Z. So that is something that happens in this reactor, right? There does exist some reaction rate between these 2 points. So maybe this is a 10-meter long tube, and we are looking at 7 meters down the tube and 7.02 meters down the tube. So in that 0.02 of a space, there's some reaction rate that applies in the fluid, and then we need to multiply it by that volume. So to define that, let's define the cross-sectional area to be A sub C. And then the volume between Z and Z plus delta Z is, of course, AC delta Z. Right, so we are assuming it's a constant cross-sectional area. It's not some kind of weird tube with tapered ends or something like that. So there's a constant cross-sectional area here, AC. So talking about that way, not talking about some outer surface area or something like that. So if you take a cross-section, the circle there, that's AC, so that's the cross-sectional area. And then in terms of the distance traveled, that's delta Z. So cross-sectional area times delta Z, that's the volume of this disk. And so the number of moles inside the space here is going to be the concentration in the space multiplied by that volume. We can also notice that we can define the linear velocity u. So there exists some volumetric flow rate through here, and we've just defined the cross-sectional area. So the volumetric flow rate divided by the cross-sectional area is going to give us the linear velocity of the fluid as it's flowing here. Right, so we can stick all that together in our balance. So we've said the number of moles in this disk we can estimate as the concentration in this disk multiplied by the volume of that disk. So let Ci be the concentration in this disk, and that will be specifically at Z. So we should say Ciz, I guess, and then multiply that by the volume here. So the volume is the cross-sectional, right? So AC delta Z. So that's an estimate of the moles inside the sub-volume. And then the flow rate into the sub-volume, so the flow into here, that's going to be the volumetric flow rate. So the volumetric flow rate times the concentration. So volumetric flow rate, again, the cross-sectional area times the linear velocity, that's volumetric flow rate, and then the concentration at position Z is Ciz, so that's there. And then the rate at which we are losing component I is the flow out here. So again, volumetric flow rate multiplied by the concentration at that point. And that concentration, again, is different to that concentration. So that's just flow in and flow out. and then there's reaction inside this disk as well. Remember, it's an imaginary disk, it's not a solid disk, so inside this little disk there applies a certain reaction rate, and if we multiply by the volume, then that gives us moles per second for the reaction rate. Note here that when we first wrote it, we wrote the reaction rate as between Z and Z plus delta Z. And now we are saying, well, if this is a very flat disk, if delta Z is extremely small and it's a very flat disk, then there's a very tiny space here. And so this reaction rate, we can say, is approximately the same as the rate at the start of the disk. So the reaction rate that applies on this interface at Z is approximately the same as the reaction rate on the inside of this very flat disk. And so instead of writing this, I'm just going to call it Ri at Z. And please note here also, when we take this this concentration, this is in principle, it's the concentration, the average concentration across the whole disk. So this should be something like Ci average between Z and Z plus delta Z. But again, instead, we are going to say, well, the concentration here is approximately the same as the concentration on average in here, so we'll just take that as CIZ. So that's rate of change of moles, flow in minus flow out, and then the reaction term. Okay, and then we can go ahead and divide by AC delta Z. So AC delta Z can cancel here and cancel here. You don't have a delta Z here, so we'll end up dividing by a delta Z. Right, AC is going to cancel on everything, so there's no more AC left over. And then we've got dCi dt equals U, and so U is a common factor here, so we'll just take out the U. The AC has cancelled, leaving us with CIZ minus CI Z to Z plus delta Z. And then we've had to divide by delta Z here. Okay, so I think you can see what this term is starting to look like. And then anyway, we've got the last term here. We cancelled AC delta Z, so it leaves us with just Riz. Okay, and then of course taking the limit delta Z going to 0, this thing you can see is a function, so it's some function at Z minus some function at Z plus delta Z divided by delta Z, and delta Z is going to 0. So this is of course looking to us like the derivative of C with respect to Z. So we can write it like this, dici di Z. Note here that it's Z plus delta Z in the second position. The standard position, of course, is C at Z plus delta Z minus Ci at Z. So we need to take a minus sign out here to get it in the standard form. So that's where that minus sign comes from. Okay, so it turns out for our plug flow reactor, it's actually a partial differential equation this time. You've got the accumulation term, and your two flow terms, your flow in and flow out, when you look at a flat disk, actually gives us a single derivative. Right? Remember, that's where this came from. If you look up here, the flow in minus flow out, it actually turns out to be a gradient across this disk. So that's there, and then the reaction term. Okay, now this balance we wrote on a specific Z position. And we didn't say anything about Z. We didn't say that this Z is only for 2 meters and you can't write this for 3 meters. So we laid no prescription or constraint on this value of Z. That means you can repeat this exercise for every Z position inside this reactor. And so this PDE then describes fully the description of the fluid across the whole tube. So that tells us that if you solve this equation, then you will know how the concentration varies across this tube. Right, so that's great. That means we have the material balance now for our plug flow reactor. Now, of course, this being a PDE, we can see there are 2 independent variables here. So we need our boundary conditions to be able to solve this. And we can easily think of the first condition. We can say at position Z equals 0. That means right at the beginning here, right? Z equals 0 over here. So at this point, we happen to know this concentration. So if you think of it, you are feeding your stream here at a specific concentration, C in, and so it's the same fluid just inside and just before this point. So that means the concentration here is equal to the concentration there, which is C in. So we can say one boundary condition is for all time, specifically at Z equals 0, the concentration is nothing but the inlet concentration. Okay, so that's nice. So at this point, we always know one value of this concentration. The second, so that kind of takes care of the time boundary condition. Then we need one for the other one. So we can say at t equals 0. So initially in this reactor, there was something here, or if there was nothing, then the concentration was 0. But initially, we can define some concentration of component I. So if there was nothing here, Ci equals 0. If there was something, then we can take samples and we can say, oh, yes, initially we had 5 moles per cubic meter in this reactor. So whatever it is, there exists some initial concentration of component I at all spatial positions in the reactor initially. So once more, before we start our reaction or anything, at t equals 0, there is some concentration of component I across the space, and we simply define it as the function Ci naught as a function of z. So that's another boundary condition. So we've got two boundary conditions and a PDE, which is first order in 2 variables, and that is sufficient to solve these equations. And of course, in our first tutorial, we'll be solving this kind of problem. Okay, so if you solve this equation, you are going to get a concentration as a function of time and spatial position z. So that is the solution for our PFR, or the solution we are looking for. Okay, now let's see if we can simplify this somewhat. So what about just saying there must exist a steady state? And always it's useful to pause and think, can a steady state exist? And indeed, there are systems where steady states don't exist, that the system keeps moving around, and sometimes it's a periodic motion, but it's still not steady state. So in this case, we know that reaction is always going to happen. The moment there are reactants there, some reaction is going to happen, and some products are going to form. And this can happen stably. So you are constantly feeding reactants here. They're constantly being converted. And what comes out here is a mixture of products and reactants. And how long we have in here decides what ratio of those we have. But anyway, that can happen steadily. So you can have a high concentration. Let's say we have 10 moles per cubic meter of component A here. And then it reacts and it goes down 10, 9, 8, 7, 6, 5, 4, 3, and then it gets to maybe 1 here, and so you've got a 90% conversion and it's coming out. So that profile can be steady. You can have a steady profile, 10, 9, 8, up, down to 1 here. So you can have a steady profile of concentration across this reactor. So it's changing across the space, but not in time. So you've got some curve here that describes your concentration, but it's not changing in time. It's just staying at the same profile. If you do go and change the concentrations on the inlet, then you'll get a wobble, and this concentration profile might shift around in time. But we are saying at steady state, we can, at steady state, going to our balance here, at steady state, we can zero this out and take this across to the left-hand side, and then the equation looks like this. So now we've reduced from a PDE to an ODE. We got rid of the time variable, so it's just a single equation in a single variable, and we can just integrate this using an ODE solver or integrate it analytically, whatever works, and we can then identify a boundary condition or an initial condition. So we can say, well, we know at the inlet point the concentration there, that's C at Z equals 0. And so this is a simple initial condition type of ODE, and we can easily solve this. Okay, so that's the steady state version of the PFR balance. And now we have these kind of weird variables, right? Velocity and axial position, we'd much rather work in terms of more familiar things like volumetric flow rates and volumes. So the first thing we can say is, well, what we already said, which is the volumetric flow rate divided by the cross-sectional area is the linear velocity. So that's how we can get rid of this u here. And then the spatial position z multiplied by the cross-sectional area, that's going to be the volume. And please note that's a variable volume. So as we choose different axial positions, we are choosing different amounts of volume. So if we choose axial position 0, then we can say that's up to a 0 volume. Then if we choose axial position 1, then it's what's the volume up to position 1, and so on. So anyway, we can define, or we can translate between z and v. And because these are both variables, then we can differentiate this and we can say dv equals ac dz, right? If you differentiate this, you can say dv equals ac dz. And so you can substitute u equals q over ac and dv equals ac dz, both these in here. And so substituting for u, so you can write q over ac there. And then in terms of dz down here, we can say dz equals dv over ac. So dv, and then the ac goes up there. And then you've got ac and ac, so those acs can cancel. And leaving us with, you can bring this q down here, and so it's dv over q. And then, of course, v over q is tau. So we can rewrite this as di ci di tau equals ri. Okay, and that together with the boundary condition, that's the system of equations we need to solve our plug flow reactor. And if you compare this with the batch reactor, you'll see there are some and with the CSTR, you'll see there are some very close similarities there. And we'll look at that just now. Okay, so there's the next part of the tutorial. So you've got the same problem, so the same sulfur dioxide conversion problem, this time in your PFR, and you want to go ahead and solve that. Use the same size reactor, I think it was 5 cubic meters. So just solve the same problem in a PFR now, and see what the conversion is at the end of that. Now, just to make a comment on these reactors, let's think a bit about this. Let's look at the CSTR. In a way, this is the dumbest kind of reactor you can have, right? Let's think about this. Let's say we want to produce all this product. We've got component A coming in. We want a lot of component B coming out. Now, let's say we did manage to get a high conversion of A. Let's say we got as much as 99% conversion of A. And you think, well, that's great. I always want to get a nice high conversion of my reactant because that gives me lots of product. But that also means then that you will have a very low concentration of component A here. So if you put in 100 moles per second of A at 99% conversion, that means you've only got 1 mole per cubic meter left here. That means your reactor then is going to have only 1 mole per cubic meter of A. That means your production rate is going to suffer. So after the first instant where you form 99 moles per cubic meter of product, after the system reaches its steady state, there's only a tiny fraction of component A here. And so you're sort of a victim of your own success here. You manage to convert so much of the reactant so quickly that the concentration here is going to be so low that your production rate is going to be extremely low. And that's a bit different to the case of the batch reactor. So initially you charged with 100 moles per cubic meter, and then as time goes on, that does reduce, and as you get to the higher conversions, your reaction rate goes down. But at least initially, you had that 100 moles per cubic meter, so you had a high reaction rate initially. So with the batch reactor, you can at least find a region in time where you had a good reaction rate here. Here, the higher your conversion, the more you are stuck to a low reaction rate. Looking at the PFR, you fed in at 100 moles per cubic meter here, and so you have a high reaction rate over here. But as you look further down the tube, you get to a stage where the conversion is so high that you've got a very low reactant concentration, and so your reaction rate suffers down here. So as you look further down this tube, you get less effective use of the reactor volume. So you can say you get a good reaction zone here and a bad one here, but at least you get some good reaction zone. Here you get the whole thing is a bad reaction zone. So to get the same productivity that you get from the batch case and from the PFR case, you need a giant CSTR. So the CSTR is a very bad user of its reaction volume. The better your conversion, the worse your reaction rate, and the greater the volume must be for you to achieve the same production rate. So those are topics we will come back to later on, but that's important to think about from right now while we're talking so fundamentally. Okay, then the other thing we want to do is go back to this definition of conversion. So we had said during the introduction that conversion is in effect the relative amount of the component that has reacted. So if we are talking about time, so initially we have some of our components, and then at some time in the future t, we have some other concentration. And so we can take the initial concentration. So let's say we started out with 10, and now we've only got 3. Then that means 7 have reacted. And so we can take that 7 and divide by the original 10 and say, well, we've got 70% conversion. So we started with 10, now we've got 3. That means we've got 70% conversion. So this makes sense to us, this definition. So we want to think about how this looks for the different reactor types we've talked about. So in the batch reactor, yes, you can just think time-wise, initially, currently. So that's how that definition works. In terms of the CSTR, at steady state, we don't have time anymore, right? When we say steady state, that means everything's constant and stable now. So there's no more change in time. So we can't compare things across time. The only thing we can do in CSTR case is to compare the concentration at the inlet with the concentration at the exit, right? So we change the definition of conversion when we use a CSTR compared with the batch. So for the CSTR case, we take C in minus the concentration in the reactor and divide by the inlet concentration. So this is 1 minus Ci over Ci in. So it's a kind of analogy. This one is more like across the reactor. This one is across time. And then in terms of this should say PFR. Please make this correction. That should say PFR, not CSTR. So for the CSTR, we are looking across this variable Z. So we have some inlet concentration, and then at the end, when Z equals L, the length of that tube, we have some other concentration. So the difference in those concentrations divided by the inlet concentration, that's the definition that's appropriate in the case of the PFR. So we understand conceptually what we are trying to figure out when we declare this X, but we need to contextualize that for the reactor. So for the PFR, this is an appropriate definition for X. For the CSTR, it's a bit different, and it's a bit different for the batch reactor. So that's how we can define X in the 3 cases. And then we can also think about the differential form. So if we differentiate X, then we can say dx equals dci. Well, so if you take one of these, So this is the time one. If you differentiate this in time, then the one vanishes, and then we are left with dci dt minus dci dt, and then divided by CIO. So then dx equals minus dci divided by CIO. And in terms of inlet flows instead, the similar thing, dx equals minus dci over ci in. Right, so now that we have those definitions for conversion, then we can say this. So first off, we are summarizing all our reactors here. So the batch reactor, we said, had this mass balance, the CSTR had this balance, and the PFR had this one. And if you look across these, you can see close similarities. So here, you've got a rate of change in time equals Ri. Here, it's a rate with respect to space-time, slightly different definition of time. And I usually call this real time, and this is space-time. But it's also equal to Ri. And then here, it's also similar. It's like a delta C. So there's a delta C, this time between outlet and inlet. And then a time, so divided by time here, and equal to Ri. So you can see close analogies among these three types of mixing, even though these are very different physical situations and arrangements. And then in terms of conversion, you also have these strong similarities. So on the right-hand side, you've got your reaction rate divided by the version of concentration that applies. In the case of batch, it's the initial. In the case of CSTR, it's the inlet. In the case of plug, it's also the inlet. So that ratio Ri over Ci at the start. And then here it's dx dt, here it's dx d tau, and here it's simply x over tau. So again, it's just a different variable. You can see the similarities here. Okay, so those are our basic material balances, and we'll come back to this and we will analyze it, and we'll understand all of this in different ways as we go in the coming sections. In the residence time distribution section, we will understand much more deeply about the differences among these types. The Levenspiel plots help quite a lot as well. And so we will come back and think about these differences more deeply as we go.